Okay, so these are notes for 3.2. And last time we graphed just ax squared, and now we're going to graph ax squared plus c. So it says a vertical translation moves the parent function f of x equals x squared, that's the one we always graph, up or down without changing it any other way. Okay, so when c is greater than 0, so this would be like plus 1, plus 2, whatever, it's positive. The graph of f of x equals ax squared plus c is a vertical translation, c units up of the graph of this. So if this is plus a number, then it moves it up. So if c is less than 0, meaning it's minus c, then it moves it c units down of the graph of that function. Okay, so if we add a number, it moves it up that many spots. If we subtract a number, it moves it down that many spots. Okay, so for example 1, we're going to graph g of x equals x squared minus 2 and compare it to the parent function, x squared. So we're going to make a table of values. The first table is for just x squared. That's the graph that you always make, so you should know those points by heart now. Even if you don't, you can put them in your calculator, not a big deal. So those are 4, 1, 0, 1, 4. Now, you can do this one of two ways. You can put g of x, like the x squared minus 2, in your calculator, just like you normally do. Or since it's just minus 2, it will be these numbers minus 2. So 4 minus 2 would be 2. 1 minus 2 is negative 1, and so on. So here's our values for that table. Okay, it says to plot the ordered pairs. So if we plot the ordered pairs, this is what it should look like. So this graph is f of x. That's our parent function we always do. Now g of x just went down 2 spots. And there's our graph for that. So it says in the comparison that both graphs open up and they have the same axis of symmetry. And our axis of symmetry on this is x equals 0. Okay, the vertex of the graph of g, the vertex for g, if we look here, is 0, negative 2. And that is below the vertex of the graph of f. And the vertex for f is 0, 0. Okay, so we can say that the graph of g, sorry, you can't see that. The graph of g is a vertical translation 2 units down of the graph of f. Okay, so that minus 2 right here just means it moved it 2 units down. All right, next page. So this is monitoring progress. It says to graph the function, compare the graph to the graph of f of x equals x squared. So for part 1, I'm not going to make you rewrite the table for x squared unless you just want to, you can. But you should know those ordered pairs. So now we're moving it 5 units down. So these are the new ordered pairs for that graph. If we plot those, these are what the functions look like. Here's our parent function like always. And then moving it 5 units down makes it look like this. Okay? And we can say that the graph of g is a vertical translation 5 units down of the graph of f. Or you don't always have to put vertical translation. You can just say, or you don't have to write the whole sentence. You can just say vertical translation 5 units down. Or you can just say 5 units down. That's fine. So our second table, it's plus 3. So if it's plus a number, that means it goes up. So now these are the new coordinates. Okay, if we plot those, we have our parent function here. And we move it up 3 units, it looks like this. All right, so you can write the sentence like we have been. That says the graph of g is a vertical translation 3 units up of the graph of f. Or if you just want to say 3 units up, that is fine too. All right, example 2. Let's see, we're graphing 4x squared plus 1 and comparing that to the graph of x squared. So now, not only are we moving it up 1, we're also looking back at what we talked about in the last section with this 4 right here. So we're going to make a table of values. If we plug those in, that's what we get. Then we're going to plot the ordered pairs. So we're still plotting our parent function, which is the blue one. But now we're also plotting these new points. And for negative 2, 17, and 2, 17, you can just put them up here somewhere. Remember, it doesn't matter. They're off the graph as long as we know it goes up that far. Okay, so we can say that both graphs open up and have the same axis of symmetry still. And the axis of symmetry, remember, is what divides them in half. So that's x equals 0. And the graph of G, we can tell that it's narrower, it's skinnier than it, and its vertex, which is 0, 1 here, is above the vertex of the graph of F, which is still 0, 0. Okay, so now we have to figure out what this 4 did to it and what the 1 does to that parent function. We know that the 1 moves it 1 unit up, and we can see that. And remember, if the graph gets skinnier, or if this number is greater than 1, then it's going to be a vertical stretch. So we can say that the graph of G is a vertical stretch by a factor of 4 and a vertical translation 1 unit up of the graph of F. Okay, so we can tell it by looking at the graph itself, like over here, or you should just know that from looking at these numbers. Okay, I want you to pause the video and try these on your own. The first one is 2x minus 5, and then you have 1/4 x squared plus 4. So pause this and then we'll start again. Okay, if you pause the video, this is what you should get for your values for number 3. And if you plot your points, we have our parent function still, which is the blue, and the red now looks like this, our g of x. So we can tell two things. We can see that, oh, it doesn't even say it on here, does it? Okay, well, we can tell that the 2, remember, it's greater than 1, so it's a vertical stretch. Okay, so we have a vertical stretch by a factor of 2, and then when you move it 5 units down, so that's how we compare it. Okay, for number 4, these were your ordered pairs. Your graph should look like this. Now looking at this, here's our parent function still. The 1/4. Remember when that number is between 0 and 1, so it's like a decimal or a fraction? That's going to be a vertical shrink, so it's being compressed. Okay, and then plus 4, it also means 4 units up. So this one's a vertical shrink by 1/4 and 4 units up. Okay, example 3. We have f of x equals negative 0.5x squared plus 2, and g of x is f of x minus 7. Alright, so this is kind of like what we did before when we start with f of x not being the parent function. So it says to describe the transformation from the graph of f, to the graph of g, and then graph f and g in the same coordinate plane. So this is when we use the two different x values here, or y values, I'm sorry. So for f of x, if we plug that into our calculator, we're going to get these values. Now, you can do this one of two ways. You can go ahead and type this in again, negative 0.5x squared plus 2 minus 7. Remember how we did that? Or you can just take these numbers here, and since it just says minus 7, you can just subtract 7 from all of these numbers. And that'll give you these numbers right here. Okay, so this is that graph, and this is the new one. Alright, so we can plot those points, and they look like this. So f of x, the first one is this one, and g of x is the red. And it says the function of g is of the form y equals f of x plus k, where k is 7. So that number right here is 7, and it's actually negative 7 if this is plus k. So the graph of g is a vertical translation 7 units down from the graph, oh no, let me undo that, the graph of f. Okay, so all you have to do is graph these two things. That shouldn't be hard. Then you just have to look at it and see what it does. Sorry, I can't stop yawning. If you look at g of x is going to tell you very straightforward what it does. Remember, if it's just minus a number, it's down that many spots. So g of x is a translation 7 units down from the graph of f. Okay. All right, and we're going to write an equation. This goes along with what was on the last page. We're going to write an equation that represents g in terms of x. So g of x is f of x minus 7. Okay, and then it says that if we plug in f of x, which was negative 0.5 x squared plus 2, this is just this. So let me see if I can get a highlighter here. This portion right here is just the f of x. So you're just plugging that in, okay? And then we combine like terms and we get negative 0.5 x squared minus 5. All right, so you're going to write the function of g. That's the first step. Then substitute for f of x, which is what we did here. And then combine like terms. So the equation g of x equals negative 0.5 x squared minus 5 represents g in terms of x, which is what we wanted. Okay, so monitoring progress. I want you to try this one on your own. So pause the video and do the exact same thing we just did. Okay, if you paused it and you did it, your first graph should look like this, and your second one should be these numbers or these values. When you plot those, this is what it looks like. So your f of x is this pink one, and then your g of x is the blue or purple, whatever color you want to call that. Okay, so before we go any further, without even looking at this graph over here, we can see that g of x is f of x plus 3. So there's nothing in front of f of x, meaning there's no like vertical stretch or shrink from what it was. There's only this plus 3. That's the only thing that changes. And that plus 3 means that the graph of g is a vertical translation 3 units up of the graph of f. And then part B, we want to write an equation that represents g in terms of x. So the first thing is to write the equation for g of x, which is g of x equals f of x plus 3. And now we plug in what f of x equals. So again, this x squared minus 1 is what f of x was. If you look back up here, 3x minus 1. So that's what we plug in, and then we just bring down our plus 3. And then combining like terms, it becomes 3x squared plus 2. Okay, so that is the equation that represents g in terms of x. All right, how much more do we have? Okay, we can finish this if I'm quick. All right, so finding the zeros of a function, it says a zero of a function is an x value for which f of x equals 0. And so a zero of a function is an x-intercept of the graph of the function. So this is what you know how to do. You just factor this. These are difference of two squares. So the square root of x squared is x. The square root of 64 is 8. So you factor it into this. One's plus, one's minus. Then we just set them equal to 0, just like we know how. This one will subtract 8 from both sides, and this one we add 8 to both sides. That's what that shows. So we get x equals negative 8 and x equals 8. Those are the zeros of the function, or where that function is going to cross the x-axis. Okay, so same thing over here. We factor out our GCF first, leaving us with difference of two squares. You can take the square root of both of those things. So that would become 5x plus 5, x minus 5. If you were to set everything equal to 0, 5 equals 0 does not even make sense. So it just goes away, and we set what's in the parentheses equal to 0. Okay, so that's what we do here. And then solving for x, we get x equals negative 5 and x equals 5. All right, so after you take these notes, your next assignment will be on big ideas, I believe. So you'll have to do that, and then you should be good for a few days or something. I don't know. But if you have any questions, just message me.